Can you hear me now?
Yes.
Okay, thank you. Okay, I think it's no, it's not time to start. Maybe it is. We have a few more minutes to go, so I will wait until everybody signs up.
Professor, I had a question.
Yes, go ahead.
Are you teaching in classes next semester?
Yes, 322.
Okay.
And now that I know, let me tell you, half of the class is going to be on transmission lines and Smith charts. Now that I know. But it's, I have to tell you that also what I found is not too many faculty in the past covered transmission lines well. So it's not the fault of the students who came somehow not as well prepared in this class at all. And I'm hoping that at the end of this semester, I'm gonna have a discussion with my colleagues. So we really try to address that in some ways. But yeah, I'm teaching 322. Since you asked, let me ask you, have you participated in the past in any classes or this semester in any classes that are face-to-face?
Not this semester.
I have one, but it's optional, and he has the class split into 2 groups, if that makes sense.
And yes, and so optional meaning those who choose, yeah. And then, so when you do this class, the face-to-face, do you also have a simultaneous attendance over the internet?
Yes. He'll, since the class is in 2 parts, the people who choose to show up will show up, and then he'll also stream the class over Zoom.
Yeah, so what they told us right now is for next semester, the classes will be, so face-to-face means those students who will be in class and the others will not be able to do it simultaneously, but in a synchronous way. So the class is going to be recorded and then placed on the web. That's what they said. I don't know, I don't have an experience of that. I don't know how it's gonna work, but just anyways, I just wanted to ask. Okay, let us try to now start with our class, worry more about us, and not now, and not next semester. Okay, what I wanted to do is, first of all, connect. Okay, connect with, all right, this is the quiz from last week. These are the correct answers. Okay, and they have to do with amplifier stability. And the correct responses, that means that you select all 3 correct answers. It says all, you see that here? All, up here. Only 20% of the class responded well. Please don't enter answers now. I will, no, I have, yes, I will unassign it. So only some people entered, so please don't. Now that you see the correct solutions, don't do that. In any case, I wanted to tell you that you may want, now that you know the correct answers, can you see them if I put show correct answers? Can you see the correct answers or not at all? Do you have access to the correct answers or not?
Usually when you make it available for review, it's possible to see the correct answers.
Oh, okay. So for example, tell me now if I do review, okay, because I always put everything for review. Okay, so now you can see it, is it? If it's for review.
I don't have it up right now. Maybe someone else
Okay.
does.
But you will be able to see them. All right. What I said.
Came up for me. Yeah, we can see them right now.
Okay, perfect. So what I suggested you guys do, now that you know the correct answers, I'll make sure they have them in all previous ones. There is nothing strange about those, obviously. The material is in the book and in my notes. So make sure that you understand why these are correct and not the other ones, why you missed some of those, all right? Because all 3 of them are correct. So that is one. Then I also had a, so this is self-explanatory, all right? So this kind of thing. Now for this other one, I only had 47 students. I will unassign it because I said that that was open until our lecture today. And here are the correct answers. And I would like now, I have to admit, this one was a difficult one. All right, I gave it to you as an exercise because I wanted you to think. And it's not obvious that we had that discussion, but I will cover some of this material today. So with this one, I'm not disappointed that only 34%. In fact, I am disappointed that only 47 students tried to solve the exercise.
Dr. Kateki?
Yes.
We cannot see this question now because you didn't post as a review.
But do you see that what I have it on my laptop?
Professor, we can see it.
Yeah. Do you see it when I have it on my laptop? Yes or no?
Yes.
Okay.
Yes.
All right. So in any case, with this one, we're going to cover, I will do an example today. And I have solved it and I will also upload it. So we will start with that. Okay, so this is top half question, exercise 18. Smith charts, make sure, please, make sure you practice with Smith charts. Don't shy away from doing Smith chart work. Okay, so this one is from, it's a fictitious problem. I created so you can see. The red line that I have here, And the green line, these are from like our homework, but they have nothing to do. The rest of the solution has nothing to do with the homework. So I just use these two amplifiers, transistors rather. And then you see, in fact, on the charts that I gave you, the value 850 and 940 are not on the Smith chart, but I have given you two charts. And by using the two, you will be able to figure out where is the 850 and 940. I gave you something that is realistic, and this is how people present it. So it's not like that I missed something. I just have to tell you, this is how materials is presented in real life, all right, from designers, the way I gave it to you for the homework. But here, to be able to see exactly what I meant by saying that it's the matching network that is critical, you need to remember that. You remember what I've said in all of this class. And I will repeat it again. Yes, the transistor changes its characteristics, mostly with the bias network. So the bias network has to be designed well. And of course, in addition with frequency. However, the transistor is nothing, it performs nothing until you put the appropriate matching networks. And what I want you to remember is that the success of creating an amplifier is not only the transistor, but is primarily the matching network. Why do I say that? Of course, a transistor that is horrible is not going to give you a good amplifier. But a perfect transistor is not, it can give you junk if you don't have a good matching network. So a lot of times in design of amplifiers, they don't, if the design of an amplifier is poor, they are not gonna accuse the person who did the device designer. They're gonna put all of the blame on the circuit designer, because exactly that's what is happening 99% of the time. Is not the transistor that failed, but is the matching, those who designed the matching network. So you need to remember that. Okay, now what I've done here is to show you why the statement that the matching network is a lot more sensitive to frequency is important. So what I did, I assumed that I looked at the transistor bandwidth. And then by looking at this here, by looking at that, you can figure out that the bandwidth of the transistor is 10%. Okay, so the center frequency is between the lowest frequency and the highest of the band, the average, the arithmetic average, or the geometric average. They are not very different practically. And then the difference in the top F maximum minus F minimum divided by F0 gives you delta F. We've seen that. Okay, 10% for the transistor. Let us now try to assume, I assume something you saw already, you will recognize that, all right? You saw that in your meter and in your homework. So this one. So let's assume we have this as an input matching network. I got something very simple. And let's assume that we wanted to design it so we start with a given input admittance. That's what happens with amplifier design. They give you, you know that as you will see, you specify your gamma in, your gamma out. So practically, you know your Y in, your Y out. And then from there, you try to match to an optimal load, which is like 50 ohms, or a source that has a 50 ohm source impedance, all right? So let's assume our load is 50 ohms. That's what it shows here. So here, from that one, you will see that this one here shows 50 ohm load. It's in an admittance form. And then what I do, I will design, as we did in the homework, in the midterm, I will design a section of line, which is this one, plus a stub, to be able then to have a match between the input impedance that I have specified and my optimal load. So the input impedance or admittance in this case, I'm working with admittances as you remember, is here. All right, so I'm doing the design at the center frequency. The center frequency is 895 megahertz. From here, I took the arithmetic average between these two. Okay, then as you know, we move along the constant VSWR circle until I come to point B. I don't hear anything, point B. And then I add the stop, so I go down. Now, why did I not stop in the first one? You know that there is also another stop down here. Okay, there is a stop. I could stop here. I didn't do that. And then this is, okay, I did not do this because I want to have, I'd rather have a longer line and then a shorter stub because I wanted to create an open-end stub. An open end for admittances is here, all right? Open end for admittances is there. So if I stop there, if I stop at this point down here, at this point, and then from there down there in the lower, the right where I am here, if I were to stop here, then I would have to go a longer distance to come to my open end, all right, which is that point. And from here to go to the open end. And that implies that I will have a shorter line, transmission line. So my line would be shorter for the first point of intersection, but I would have a much longer stub. I'd rather have a longer line and a shorter stub. All right, because if the stub is too long and it's gonna, sometimes if it's too long, it may radiate because then it looks like a half dipole. So, okay, so shorter stubs preferably and longer lines preferably. If one of the two has to be longer, obviously. I cannot make both of them short. Okay, so I go up here. I go to this point B, and from B, I go down to the center of the chart, where is my 50 ohm impedance or 1/50 admittance. Okay, now what I will do is simple. I will keep the same dimensions and I will see what is gonna happen to this matching network if I change frequency. Obviously, in fact, I have to say that is going to be the other way around that I have it here, sorry. Excuse me for my mistake here. Why do you think I noticed that I made a mistake there? Why did 850 has to be first and 940 second? Because when I go to higher frequencies, the wavelength becomes shorter. So a given physical length with shorter wavelength is gonna be more wavelengths, all right? A bigger fraction of a wavelength, do you understand that? If I go to higher frequencies, my electric dimensions become what? Smaller, larger, or lower? Or smaller? What is that? Again, I have a fixed physical dimension. It's the length of a line. I fixed it at the center frequency, which is 8. The center frequency is 895, okay? And I fixed that there. And then I change the frequency. So the physical length, that is say, for example, 0.2 lambda at 845 megahertz. How many lambda is it gonna be at 940? Is it gonna be more, a bigger fraction of lambda or a smaller fraction of lambda?
More.
more. Exactly, because lambda now becomes smaller, all right? So 940 had to be up there. Okay. So at 850 is gonna be the lower point that shows here. At 940 will be there. And then I do the same. I look at the physical dimension of the stub. And that's here, 850, 940. The same thing applies then to the dimension of the stub. Smaller, fewer wavelengths when I go to the lower frequency, more wavelengths when I go to the higher frequency. All right, so eventually my points go from 850 there to down here, and then from 940 up there to 940 down there. Okay, so now what I'm gonna do that I found what kind of, I'm not gonna go obviously to the center of the chart, all right? So practically my matching network has changed. So it does not match anymore 50 ohms, it matches another impedance. So I'm now going to 850 and 940 and look at those two impedances. All right, and that's what I do here. And I find in admittance form, obviously, the difference between the minimum and the maximum impedances that now, obviously, the physically fixed matching network electrically now has changed, and it matches to different impedances than an impedance of 50 ohms. And now I'm taking the ratio. I do it in admittance form because it's easier from the Smith chart. And what I find is that the ratio of YL max over YL F naught is 1.6. So I move. Instead of 1 is the center of the Smith chart, all right, where the impedance that I'm matching is the same with the 50 ohm impedance of the line. So in admittance form, obviously, the same thing applies there. And I now change from 1.6 to 0.8. How much change in the impedance that shows? 80%. Do you see that? I'm changing my impedance by 80%. This is how a 10% change in the transistor over a frequency range, it's only 10%, the transistor, but my matching network changes the impedance that it can match by 80%. What does that tell you about the matching network? It's very narrow band because it changes so fast. It's not like your filters, all right? You design some filters that they had good pass band and everything. This one is not gonna match unless you're right at the center frequency. And then the moment you move away, then you lose that matching. So the matching network is very sensitive. And that's a lot of times when we wanna develop broadband designs, as you will see, we don't try to change the transistor, but we will change the matching networks. Is that clear as a concept? Yes or no?
Yes.
Okay, please go through this. I don't expect you to remember, it's well written. So I will upload this and you will find it as both under the question and in the topics we covered today. I would like you to read that because it gives you practice with the Smith chart as well.
I have a question.
Yes.
In the Smith chart, those arcs, the red and green arcs, like 850 to 940 gigahertz.
Yes.
Can you explain how does that, I mean, what does that mean in the Smith chart, that line?
I don't understand that. you're talking about the transistor?
You have a line there to 850 gigahertz to 940.
Are you talking about this one?
Yeah.
Yes, okay, that belongs to the transistor.
Okay.
And this one
right.
too. This shows how the transistor changes, nothing else.
Now, what about the green one next to it?
Wait. You're talking about this one? I'm sorry. Wait a second. You're talking about the green one here?
The S22, I think. Yeah.
S22. This is what I gave you in the homework. These are the characteristics of the transistor.
All right. Okay.
Why are they placed there?
What?
Why are they placed there?
Why are they placed there?
Yeah.
Because I wanted to show you how the transistor characteristics vary out there and how much your matching network is going to vary over frequency. I don't need them practically. The only reason you need those is to find out your gamma in and gamma out. But I only put it there because, of course, I asked you a question, all right, in the exercise, and the question was, what makes mostly a narrowband design? Is it the transistor or the matching network? And the answer was like the matching network, all right? Mostly.
Did you say that like the two arcs, the 940 arc and the 850 arc, are kind of showing how the transistor changes and how if you have the same matching network, it's not going to be able to compensate for those changes? Is that what you're trying to say with this?
The matching network, as a matter of fact, can compensate if, for example, your frequency was fixed, but the transistor would change for some reason, for some other reasons, not the frequency, all right? A fixed matching network with some variations in the transistor S parameters can still match well. But if you have a change in the frequency, then your matching network by itself changes so much faster than the transistor characteristics that the failure of a design to be broadband is not because of the transistor, but it is because of the matching network. That's the concept I wanted to show you. Which means now that I have an exercise here where the transistor changes by 10%, I took a design of this transistor and I showed you that if I design it for the center frequency, but then I change the frequency, the transistor changes by 10%, but my matching network changes by 80. That's all that I wanted to show you. Is that something, do you understand that, what I'm trying to tell you, the concept? Or
yeah, the match network is more sensitive to frequency.
Yes, yes. What I want you to do is to spend time to read that and to understand it. And if you have difficulty understanding that, to see me during office hours. I mean, this is important because I want you to feel comfortable with the Smith chart. You cannot do anything without the Smith chart when it comes to an amplifier or an oscillator. I don't know how else to tell you that. And I think I told you that from the beginning, all right? That Smith charts and transmission lines are so fundamental to circuit design. You cannot avoid it. You cannot do circuit design without having to deal with these concepts. Okay, now I would like to go quickly to stability circles because I started that last time. Did we not? We started stability circles last time. And what I decided to do very quickly, I don't want to repeat the whole thing, but we started here. We just said last time that there are two different conditions in the transistor. It's like the unconditional stability, and then we check it mostly. We said most recent work and books or papers, they don't check both K and delta, but they check this one. This one. That's what they check. And if that's above 1, the more it gets above 1, the more stable it is, obviously. But you know, if it is above 1, clearly, it's not like 1.001, for example, but it is above 1, then the transistor is considered to be unconditionally stable. And if M is higher than 1, or excuse me, less than 1, then it's conditionally stable. And what do you mean conditional and unconditional stability? That's what you need to read. And that's why some of you missed some of the questions in the quiz. So I want you to look at those tables really well. Okay, conditional stability. What is it important for conditional stability? That we make sure that the input reflection coefficient magnitude and the output reflection coefficient magnitude are less than 1, okay? And it shows the graphs here. Now, remember we talked about input and output stability circles? There is a confusion about what people call input and output. So sometimes people will call, you will see some, they are flipping sometimes these between books and in presentations. So what we are gonna call them is gamma L plane and gamma S plane. And that is gonna be clear of what it is. The gamma L plane is where we find these L circles, CL and RL, okay? That is called the gamma L plane and is this one. You will always call that the gamma L plane. And you're gonna have the center CL and the radius RL. And if the amplitude, or the magnitude rather, of S11 is less than 1, then stability is inside the Smith chart where it is pink here. And if the magnitude of S11 is higher than 1, and we discussed last time why it can be higher, then stability is achieved in the overlap. And if for some reason there is no overlap and S11 is larger than 1, then you cannot stabilize this transistor with the techniques that we have. Something else you need to change is bias point in that case. You cannot stabilize it with RF design. You will have to go into its DC bias network and change that to be able to stabilize it. Gamma S plane, now we're gonna call this one, where we have CS, RS, and now we are looking at S22, and if S22 is less than 1, then stability is inside here, and that's where you check all of your gamma out values. That's where from where you have to select a gamma out. And here stability is gonna be only in the overlap, and that's from where you will have to select the gamma out. As you can see, in both gamma out, which is the gamma S plane, we call it, and the gamma in, which is the gamma L plane, we are looking at gamma in and gamma out magnitude to be less than 1. If for any reason or under any circumstances, the magnitude of either gamma in or gamma out or both is higher than 1, then you don't have a stable amplifier. You have an oscillating device. Might not even be a good oscillator, but it oscillates. Okay, now last time somebody said you did not know how we were plotting the CL and RL circles. Is that right? There was a misunderstanding, I guess, last time how we do that. Is there still anyone who does not understand how we plot them? So I go through this example, or should I let you read the example?
Can you go through it?
Yes. Okay. So now we have to design an amplifier. The first thing you do when somebody gives you a transistor and they ask you to design an amplifier is to do what? Before you do anything else, forget about everything else, is to find out whether it's unconditionally stable or conditionally stable. And then you have to find your stability regions, okay? Nothing else before then. You're not gonna try to do anything else before you are sure of what are your gamma S and gamma L planes. Okay, so in this case, we give this transistor here, this one, and I assume that this is a unilateral transistor, and I do it for simplicity. And you will see later that it's a very good assumption when it comes to gain, that you can have, if it's the S12 is very small, there is a parameter you can check to make us to assume that it's 0, because then all calculations become very simple. So I assume that in this particular case for us to move forward. And then I found delta, and I found delta, and from there I found nu. And then for that, I found mu is less than 1, all right? In fact, in this particular case, I did, before I assumed it's almost 0, I did the calculations, but I found it less than 1. Okay, so now you have, if, for example, mu was above, is 1.2 or above, I put it that because the book has has a discussion on this. Okay, so now in any case, in our case, mu is less than 1, so we need to find out what are our stability places. Gamma S plane. So I find C sub S and R sub S. Okay, I calculate them. Now, what I found is that C sub S is on a line here. C sub S, let me write them down. C sub S is here, you see it? 1.132 and has 68 degrees phase. So it's a complex, it's a point on a plane and it's in polar form. So how do we measure it? The dimension for CS, you see that ruler that we have in there, that we used it for reflection coefficients. You see that here. I'm sorry, I covered it up, this one. Here, this one. I'm using this ruler. It's a linear ruler. And it goes from 0 to 1 on the Smith chart, but if you are to extend the Smith chart, because now we are going up outside of the Smith chart, all right? Because we are dealing with active devices, with amplifiers. We're not dealing with passive circuits. We have active device in there too. So then I go and I measure. So how much did I find for CS? 1.132, okay? So what I do, I go here, if you have a ruler, electronically or physically speaking, say my ruler here will be this one. So approximately 132. You can also extend it with air. Then this one is gonna be the distance, all right? So what I did, I put this line here, I changed it accordingly, and I got this to this point. See? So I found the place for CS, but also it has an angle. How do I measure the angles? I measure them, if you see, angle of reflection coefficient. It starts at 0 here, that point, 0, and it goes to 5, 10, 15, 20, 25, 30, no, excuse me, the other one, reflection. 0 here, it goes 10, 20, 30, 40, 50, 60, 70, and then it's 60, we found 68. So the angle here, if I were to extend that green line, so it would cross exactly this yellow rim that I have, colored with yellow at 68. So with the distance that I have measured with my ruler and with the degrees that I start 0 here in the place where all of the circles touch, then I find C sub S. Then I find R sub S 0.199. So I go down to the ruler and I measure 0.199 is about 0.2. So practically I measure from here there. Let me see. Okay, that kind of distance. And with this kind of distance, I create the circle. There is an intersection between this little circle and the Smith chart, the primary circle of the Smith chart. And because S22 is less than 1, then it's all of the green area that allows me to select points for gamma out. All right, all of this area, the green area, allows me to select the gamma out. So I could select any point, and then I will have a stable transistor. Now I might not have a good gain, but my amplifier is gonna be, amplifier is gonna be stable, okay? And then, in fact, you could do exactly the same thing with the CL plane, but I did only one as an example. Is that clear? How I drew the circle?
Yes.
Okay.
I have a question.
Perfect. Yes.
If the small circle never touched the Smith chart circle, so we say it's never stable?
No. It's unconditionally stable in that case.
It's unconditionally stable. Okay.
Yes, because everything on the Smith chart practically shows you that every passive impedance can stabilize the amplifier. All right? Because the Smith chart shows every possible passive load. Every possible passive load, any passive load, then will stabilize it. So that is unconditionally stable. However, if S22 is larger than 1 and the circles do not intersect, then you have a device that cannot be stabilized. So you have to go and change the bias network, all right, of the transistor.
Yeah, thank you.
Okay, perfect. Any questions? Now, I found this an interesting Smith chart, you guys. This is it's colorful, so I used it anyways for this example. But here is an example that I have in detail, and I would like you to read it. But here is what we wanted to start discussing, and we will finish it next time. Also, I wanted to tell you we're going to have an example that I'm going to activate right now and impact right after this, my office hours rather. And you will have until Friday. It's going to be on issues around stability and also look at the unilateral gain. And so we're talking about that here. We said, you remember where we said that in most cases, the transistors are biased. Not all cases, obviously, but in many cases, let's put it this way, not in most, many cases to be like more accurate. The transistor is biased and it's biased in a way that S12 is very small. Okay, therefore, it is in many cases, it is possible to assume that it's 0 to simplify a lot of things. And then, so we are talking about having a unilateral device. What allows you to make this assumption that S12 can be assumed 0 is this figure of merit that is called the unilateral, rather, figure of merit. Let me see. Unilateral figure of merit. All right. It says here, it shows here the expression for that. And the figure of merit gives you an error you're gonna make. Because it gives you an idea of how much error you're making if you make this assumption. And that's exactly what will drive your decision to make this assumption. So if you have a unilateral device, the transducer gain for the unilateral device is what you're gonna get if S12 equals 0. Without that being 0, you're gonna get the transducer gain. Can somebody tell me what is the transducer gain? How do we define transducer gain? Do you guys remember, girls? Can somebody tell me? What is the transducer gain?
Is it when they're simply matched or with simple matching?
Yes, correct. But how else do we also, it's the ratio. I mean, before you go to matching, I would say transducer gain is the ratio of the
load over source.
Exactly. The power that is dissipated by the load by the power available by the source. Okay, that's your transducer gain. What is the one that you said, which is the GTU, the one you made reference to, rather? So let's see, we'll go to here. Sorry, from this one, I don't wanna get you dizzy. All right. Okay, transducer gain, power gain is this one, you see that? And that's what it gives you. It is PL over P available by the source. And this one is, this is the transducer when it's defined by S12 equals 0. Yeah. What's that?
I'm seeing a
white on the screen. Yeah. Right. Yes, I wear glasses so I can see well without my glasses. Okay, let me see. So definitions, power gain, maximum available gain, that happens with the complex conjugate matching, transducer gain, okay, and so forth. Let me see. What else we have? Nothing else. Okay. There is more, obviously, but that. So, in any case, this gives you an idea. So, on how much you are compromising your solution by doing this. And then here, also, there is a guidance that we get that if you find that your U, this is the unilateral figure of merit, if this U gives you a 10 logarithm of this 1 over 1 minus U squared to be less than 0.3 dBs, meaning that this one here, the mistake that you make by going to unilateral transistor is relatively small, all right? So you underestimate or you overestimate your gain by 0.3 dBs, which is kind of a very small number in all things considered. So within the 0.3 dB, within that space of error, then you can simplify your calculations by assuming that S12 is 0. You don't do it, of course, when you calculate U, you do it after you calculate U. Okay, now let's assume that we do that. I did it to simplify things. And then what I did is, what we do is that we get this. Now at the center, your yellow is the transistor. This one is your transistor. This one is your output matching network. This one is your input matching network. And we define three gain functions. One is the gain of the input matching network, GS, and is given here by that. And that's number less than 1 because it's a passive network, all right? So your GS is gonna always be less or equal to 1 maximum. Equal to 1 if you have no losses. And that's never true. In reality, it's always less than 1. The question is how close to 1 the gain is. Then GL is also less or equal to 1. And G0 can be less or higher than 1. Of course, you would like to have a large S21 because that will give you higher gain. And then it's the magnitude of S21 to the second power. And then when you calculate those things in numbers is gonna be the product of the three that gives you the transducer gain of your device, the product of the three. If you calculate each one of them in dBs, it's gonna be the sum of the three, all right? Sometimes you will tell you, people is gonna tell you, G sub S is, if it's gonna be less than 1, in dB is gonna be a negative number. GM, G sub M, I should say G sub L here. I don't know why I put M. G sub L is gonna be also negative, and then G0 is gonna be positive, so you sum them up to find G sub T. But if it's numbers, not logarithms, then you multiply them. Okay, now we go for, we know that to maximize the gain of this amplifier, we go for conjugate matching. And then in that case, we get the values of GS max and GL max, all right? Meaning the GS and GL, we call them max because they will give us the maximum gain. And then we find these by these expressions. And from there, we introduce two gain factors. Again, these gain factors is just the ratio of the two GS and GL over the maximum expected values, and they're given here. The two gain factors, obviously, they will be less or equal to 1 and larger or equal to 0 because of the way we have defined them. And because of that, it means that GS and GL represent circles. So as we did for the stability circles, we also find here circles for G sub S and G sub L. All right. Now, I want you to read this example in the book, but I have a different example here. So I will show you here briefly how they look, and then we are going to do this example next time. But what it shows here is the following. So here is what it happens. First of all, we check stability. All right, this is unconditionally stable. So now we know that we can select, in this particular example, it is unconditionally stable. So now we know that we can select any point on the Smith chart for gamma L and gamma S. But what point are we gonna select? There are many more conditions that we will need to satisfy. one condition is to select the gamma S complex conjugate to be equals to gamma in and gamma L complex conjugate to be equal to gamma out. And that is fixed, and this is going to give us the maximum gain. But when we want to make a broadband design, so we want to go outside of the maximum gain. So for a broader band design, that implies that we will compromise our gain and we'll say, okay, instead of the maximum gain, I want to have like, if the maximum gain were to be 8 dBs, I would like to design something for 6. So practically within your band, you're going to eventually go to 8 dBs, but you're going to have a much broader bandwidth in which your gain will be equal or above to 6 dBs. And then with that, you have to narrow down the values of gamma L and gamma S. So by plotting these two circles, we always, as you will see, select the point that intersects between the line that connects the center of the circle to the center of the Smith chart and the circle itself. And we will get the point that goes the closest to the center of the chart. And then the same thing with gamma L. So from all of the possibilities that will give us, so the point, the points inside the circle will give us gain equal or higher than 6 dBs. In that case, whatever we set as our goal. Or inside the other circle, the C sub L circle will give us, inside that circle will give us higher than a specified, a desired value. And outside will give us lower. So we want to stay at least on the periphery of the perimetry of the circle, but we want to have the least possible magnitude of gamma S and the least possible magnitude of gamma L. So we want to go as closest to the Smith chart as possible. Why is that? Because if we have to match a very high in magnitude reflection coefficient, and then the value of the reflection coefficient, gamma S or gamma L, is going close to the edge of the Smith chart, then the further out you go from the Smith chart, the center to the edges for these reflection coefficients, the more narrow band the matching networks become. So this is the reason we try to select the lowest possible magnitude of gamma S and gamma L, which already allows these points to be on the two circles. So can you guys see? People say that you cannot see anything. What does that mean?
I can see the Smith chart.
Can you see the Smith chart?
Yes.
I can see things perfectly fine.
Okay. I saw somebody chatting that they could not see it. Okay, we're gonna solve that next time, but I wanted to take you through this process. And my advice for you is just try to go through these equations. They seem to be kind of intense, but at the end, the methodology is very similar, right? For amplifier design, we always have to do these circles. We do circles for stability, circles for gain. We will do circles for noise. That's how you do. That's how, and all of them looking to stay within the Smith chart to be able. So at the end, all of this is happening because we want to find the right values for gamma L and gamma S that will give us what we want as gain plus what we want as noise, because at the end, all right, at the end, the amplifier needs to do more than one thing. And an amplifier that gives maximum gain, which is one thing that we've seen how to do it with conjugate matching. It may also give high noise. And for low noise amplifiers, we would like to have as high as a possible gain and as low as a possible noise. Now, these two do not necessarily go together. So we will have, that's why designs is like a trade-off, all right? You trade off your gain for low noise. And then you have to find all of these processes that we see, like which are like kind of a recipe rather for now. They help us do this kind of trade-off in the design and find the right points for our designs. Okay, so that's the basic idea. And I would like you to read this part so we can cover it next time and then look at similar circles for low noise as well. Any questions before we end today?
Do we have exercise?
I said I will turn it on right after office hours, and you will have until Friday.
Next lecture, right?
Yes, yes.
Okay.
All right.
Is that like before next lecture or after?
No, before, by the time we get in the lecture. You
Okay,
guys need
sounds
to
good.
have it done. Okay, because then I would like to talk about it in the lecture, right? Hopefully. Yeah. Okay. Thank
I have
you.
a question about the how to find the stability circles.
In this particular case, this is unconditionally
Yeah, I know, but whenever you're finding the center of the stability circle,
yes.
Whenever you're trying to define, when it comes to the length of that line, do you use one of the rulers on the bottom of the Smith chart?
Yes, this one. Yes, I'm using, I'll tell you, the ruler for the reflection coefficient, this one.
Okay.
Okay.
All right. Thank you.
Okay.
Dr. Katehi?
Yes.
Can you go back to quiz 10 really fast? I just have a quick question on that.
Sure. Yes.
When I was reading B and D, and I think that the results of this kind of showed this, I thought that like B and D were very similar, and then D was just kind of more specific, which means that we shouldn't put B as the answer. And then since 37 people put both B and D, or B and D, and then only 10 people got everything right, it seems like there's a lot of confusion here.
No, I think
on like what the difference between B and D is, or the similarity, or
there is a fundamental difference between B and D.
Okay.
B says that an amplifier is stable when, I should say, the reason is, these two are less than 1. And then when I make that statement, it implies that gamma in and gamma out can be less than 1, either for all impedances or for some. I don't specify. This is a correct statement. If somebody, so what I say here, say identify all correct statements, not some. If you have two that are very close and they're both correct, you have to identify them.
Oh, okay. Because I guess my thought process was like, if it's unconditionally stable, then it doesn't matter what gamma in and gamma out are. They could be anywhere on the Smith chart. But then for D, that consideration comes in when you're talking about conditional stability, which is the condition being the gamma in and the gamma out.
It says, I only asked for correct statements. I did not say, if say somebody would tell me, identify all the correct statements. I will look at the first one and I would say that's not correct, all right? Because we don't define unconditional stability like this. Then I look at the B and I say, yeah, that is true. The amplifier could be either unconditionally or conditionally stable, but it's a correct statement because these two conditions make the amplifier stable. And then I go to C. Amplifiers are conditionally stable if this is not correct. And then I go to D. An amplifier is conditionally stable if some passive sources, this is a correct statement.
Yeah,
That
yeah,
is,
okay, okay.
Okay. So
Yeah, I see it
what
now.
I said is identify all correct statements. Some of them, I mean, you only dismiss those that are incorrect. That's what it says.
Yeah, I think I just read too much into it and thought that it wanted, since there was a different answer that specified that's conditional, that I shouldn't put B also. I guess I just kind of thought too much about it there, but just looking in the future at what is inherently correct.
Yes, when it says, you know, here, what I try to emphasize here is the following. When we write things in engineering, it's not like in liberal arts, where you write a sentence and then you have flexibility to make interpretations. In engineering, writing is precise. You read it the way it is. You don't imagine things. All right, see what I'm saying? I mean, in other literary writings, you have a flexibility in your understanding and your interpretations. In engineering, we don't have that flexibility. And why is that? Because when you read engineering documents, it's like law. You have to read it the way it is. You read it and you reread it, and then you try to find everything according to what it says, all right? You cannot give less, you cannot give more. And that's why I insist, because I've noticed, and in my, I don't know why that is, and maybe it's part of our training right now, but I've noticed that many students have difficulty reading with discipline engineering readings. We read them, we should not read them like a novel or something, all right? Where, like we do in other disciplines. Here, for example, when I say identify all correct statements, it just means that. It does not mean more, it does not mean less. Even if I had two statements that were identical, you would have to identify them. See? And then
gotcha.
there is a reason for this. For example, later when you do system design, some of the specs are like 30 pages. Some of the specs for systems can be more than that. Some of the specs for components can be just 2 pages. Just a simple component to have a spec that is 2 pages long. You have to really read what it is. You cannot see more into this and you cannot see less into this, all right? So it's very disciplined reading and it's accurate, and the way we write it has to be accurate also. That our writing has to be accurate because others will try to read it accurately. And if it leaves space for interpretation, then they will not be able to understand anything. So that's the kind of thing. It's training, you know, so we are trained right now for that. Okay.
Yeah, thank you. Thank you.
You're welcome.
See you, Professor.
Okay. How do I do that?